Today what we'll be working on is properties of lines and circles. So you recall that we talked about chords and radius and segments and various things that dealt with circles. The first property we'll deal with is chords and their distance from the center of the circle. For chords, there are two statements that focus on that. So now what we're going to do is we're going to label each of these points. We'll call this point A and this one point B. So for 1A, if you think about it, it's basically talking about the distance of a chord from the center of the circle, and basically that's going to be focused on by this little dot that we have here and this little dot that we have here, and it's all related to the center of the circle, which we find right here. So if you think about it, if I notice that this distance and this distance are the same, then we can easily say that the chords are the same length. We'll label this point and this point F and G respectively. Now try to remember that the chords are going to be along these lines here. So these are the chords we're looking at. And we're saying that the distance from here to here are exactly the same distance. So what that means is if OF is equal to OG, the distance from the center to the chords, then the chord lengths AB and CD are the same. The peculiar geometry of the circle also guarantees that if I have the same chord lengths on the edge of the circle, that means we will have the same distance from the origin to each of the chords. Geometrically speaking, what we're saying is the following. Take a look at the graph on the right here that has S and T on it. So we're talking about this graph right here. Basically what we're saying is that these chords, if they are the same length, then we can easily guarantee that these two distances that we have from here to here and here to here, i.e. where it just touches the chord that we have here, are going to have exactly the same length. We'll take a moment and we'll label all the edges of all the chords so we have a nice equation and a nice statement. We'll label this chord A, B, and we'll also label this chord C, D. So this time we'll relate the chords to each of the distances. So if AB equals CD, then OS equals OT. For property 2 of circles, we're going to have an amazing result. Do you remember that thing called a perpendicular bisector? We learned about that in grade 9 and 10 when we were dealing with lines. A perpendicular bisector is a line that slices another line exactly in half at a right angle. So imagine, as usual, we're always starting from the center of the circle. Now what we're going to do is we're going to actually draw a straight line from the center of the circle as best we can to the edge. We know that that's called our radius. Now, if we can guarantee that our line is actually our chord that actually crosses this radius is exactly at 90 degrees, we can guarantee that the chord is actually split in two. Let's label the chord and the lines. The chord will be labeled AB, and the perpendicular bisector, the point where it crosses, is going to be labeled D, and the origin will label it O. In essence, when we look at this equation, when we look at this picture, you kind of get a hint of what's about to happen. If you have a line that perpendicular bisects the chord, we end up having two equally broken line segments. In essence, we have AD equaling DB. And that's what property number 2 is talking about. Property number 2 basically just says a line from the center of the circle that meets a chord at the right angle will bisect the chord, split it in half, and the right bisector pass will pass through the circle. And if we think about it, if you find a center line that goes through the center out to the edge of the circle and it's a right angle with a chord, you've got the same property going the other way as well. So if I have a line that goes through the center of the circle and is at a right angle with the chord, we can clearly see that the chord will be split in half. Part 3 is talking about tangents, so is part 4. If you look at part 3, it actually says I've got a tangent that's actually sitting on the edge of a circle. Now, what we can do, when we have something that sits on the edge of the circle, we can guarantee that if the line that makes contact with it, i.e. this one right here, as long as it goes through the center, you're going to have a perpendicular contact with this line. That's why it says a line that's perpendicular to the tangent will pass through the tangency and the center of the circle. That is what you can guarantee. For part 4, it says that two tangents that are off, that are touching the circle, that go through the same point, will have, in this case, this point here, will have exactly the same distance, or same length from A to C and B to C. That's all it's saying. There's nothing really to it. Now we're just going to go on to the next page. For idea 5, we're just taking a look at these peculiar inscribed subtended triangles. If you take a look, this is the chord that we're talking about. This chord is key to the entire problem. It says here, for number 5, if a central angle and an inscribed angle are subtended by the same chord and are on the same side of the chord, then the central angle will be twice the size of the inscribed angle. So what it's saying is that if I have an angle on this edge and then another angle on this edge, if this was 40, then the one that's farther away on the circle tip, on this edge of the circle, is going to be half of that. So if this was 40, this one would be 20. Now if I look at this circle here, these two angles aren't on the same side of this line. Basically, they have to be on this side here. So if I wanted this corollary to work, I would have to have another triangle on this side, and I would have to essentially find a way and get rid of this. And if this was, say, 120 degrees, this angle here would be 60 degrees. But you need to make sure that those two angles are on the same side of this line, this chord that both of these angles touch. So basically, with idea number 5, you need to make sure that the angles are on the same side of the chord, or the whole thing just doesn't work. Moving on to 6 and 7. Let's break 6 into 2 parts. Again, just like the original first 2. Basically, we have equal chords subtend 2 equal angles, and equal central angles subtend 2 equal chords. So now what we're going to do is we're going to take a look at what would happen if we actually took a look at part A. Now part A says, imagine if we have these 2 sides being the same. That means these 2 angles here would also have to be the same. That's what 6A is talking about. So now, suppose that I have 2 central angles, i.e. these 2 angles are the same, then the chords that are on the edge of the circle will be the same. For number 7, it says, equal chords subtend equal inscribed triangles. Equal inscribed triangles subtend equal chords. What it's saying is, if I can guarantee on the edge of my circle that 2 edges, 2 chords that touch the edge of the circle will form identical angles on the opposite side of the circle. That's it. If you take a look at those 2 angles that are on the opposite side, you're going to find out those angles will be exactly the same. Moving on to 8. So, suppose I have 2 inscribed angles. So, we're actually talking about D and C. If they share the same chord, so that chord here is going from A to B, that means this and this, the 2 angles that are farthest on the edges of the circle, will be the same. We'll also share opposite angles. Do you remember that opposite angles thing? If we had 2 lines that crossed, you had opposite angles being the same. So that means those 2 red dots have to be the same as well. Guess what else is going to also have the same angles? Notice the 2 X's in the corners. Those triangles are also going to be the same. So when I was talking about these triangles, I was actually talking about these ones here. This and this will be the same. But most importantly, it's these angles that you'll know will always be the same. We start with that, and then we go with the inference of these to find these 2 as well. For number 8, it just says that if I have a triangle that has a hypotenuse that goes across the center of a circle, and you know that anything that goes, a straight line that goes all the way across the center of a circle, is called the diameter. That means any triangle that you create here will always be at a right angle. It's a very peculiar property, but it works. So we're going to take a look at this circle. And because of this chord, if you take a look at it, X has to be 40 because it shares the chord, which means that this triangle, that these 2 triangles have to be the same. And that was from fact 8. Now, if you take a look at your sheets, you'll notice that on your sheets, one of the corners here is 25 degrees. That is this one here. Now, because of the chord that could be formed from C to E, that would mean that y is also 25 degrees because of fact 8. So you remember that this corner and this corner would have to be the same if this was my chord. So that and that have to be the same. So now we have to find angle Z, period. What I'm going to do is I'm going to look for this angle right here. And we know that this angle is supposed to equal this angle up here, right? Now you know that the entirety of a circle takes up 360 degrees, right? So if we went all the way around here, this would be 360. So we're going to use an indirect method to find Z. I'm going to come up with a new letter and we're going to put in a side for it. So I can't really draw in there, so what I'm going to do is I'm going to zoom in and kind of put a little arrow here. So this arrow, we're going to call this corner fish. Yeah, let's call it corner fish. Now, on that triangle, you know that fish would equal 180 degrees minus 40 degrees minus 25 degrees, which equals 115 degrees. Now, you know that every straight line has a total of 180 degrees. So now we know that this spot here is 115 degrees, isn't it? Now, because that's 115 degrees, right? That means if I wanted to find this angle, I'm going to call this angle my happy face, because it's going to get me close to the end. I want you to think about what that means. If I wanted happy face would have to be would equal 180 degrees minus 115 degrees, which is just 65 degrees. Thank goodness. We're so close. I have to have a happy face. Now finally, if I want Z, Z is formed by a triangle here, isn't it? And we just found that happy face was equal to 65 degrees. Oh my goodness. Well, what that means is, if you think about the triangles, a basic triangle that we've studied, every triangle has 180 degrees. So that means angle Z is equal to 180 degrees minus 65 degrees and minus the 55 degrees that we already know inside this triangle. Which means that Z is simply 60 degrees. For part B of this problem, you'll notice that we have two tangents, right, that meet at the same point. This refers to fact number 4. It said that if we had two lines that basically were tangent, that touched each other at the same point outside of the circle, that they would be the same, that the sides would be the same. So x equals 9. Notice that angle B actually originates from the origin and hits the edge of the circle. Now, we had something that talked about that. We know that angle B must equal 90 degrees. I guess I should say what each of these four are from. So this is from fact 3, that any line that comes from the center goes to the edge is perpendicular to the tangent. And then this first one here is just all about fact 4. Now, since this portion here is 90, and this is 35, I should be able to calculate this y value, because the internal angles of a triangle are 180 degrees. That means angle y is equal to 180 minus 90 minus 35 degrees, which equals 55 degrees. So angle y is 55 degrees. Now, you remember that triangles have to be congruent because you need to have a side, and an angle and a side. So if you take a look, this angle and this side and this side are the same. This angle and this angle are the same, and they also share a side in the center. So therefore, these triangles are congruent. Therefore, W is also equal to 55 degrees, and Z is also equal to 90 degrees. But that's also from fact 3. Now we'll move on to example C. We need to determine the length of OP in part B. Trust me, draw the triangle. Always draw the triangle. This problem involves a right-angled triangle, so we need to use SOHCAHTOA. Label your sides. In this case, we'll use cosine since we have the adjacent and the hypotenuse. So you need to remember that when your variable's on the bottom, cosine goes on the bottom of our ratio. If the variable was on the top of the ratio, then cosine would have been times by it. So since we have no units, you're just going to have to say h is just 11.0 units. So what we'll do is we'll quickly draw the triangle again, since we have all the information we need. We have 9, we have 11 here, and we have, here's P, here's B, and here is O. The radius of the circle is going to be OB. Now, we have a right triangle. Let's just use Pythagorean theorem. We'll also label this bottom portion R so we can calculate it. And we're done. Now your homework is on the next page. So do as much as you can. You'll have until the end of the week to complete all 5 lessons.